Supercomputers provide us with the capacity to calculate intricate algorithms that help us in scientific fields from pharmaceuticals to weather forecasting. So it's important that supercomputers be at their peak performance in order to give us the fastest results. That's where computer chips and laser developing technology comes in. Integrating optical processing into electronic chips holds great promise for high-performance computing. Electronic devices are very good at processing information because electrons interact strongly with each other. However, as electrons are moved to transfer information, those interactions also cause background noise and weaken the signal, and so cutting-edge chips are pushing the limits of what electrons can do, carrying signals on circuit boards and in chips themselves. In contrast, photons have little effect on each other, so they can transfer information much more efficiently than electrons. That's why fiber optic cables have replaced wires in the main circuit boards of high-performance computers, as well as in extremely long running cables. Computers suffer a critical limitation when it comes to working with light. However, silicon can transmit and detect light signals, but it can't generate light efficiently. Compound semiconductors such as gallium arsenide and indium phosphide are needed to make proper working lasers. Chip maker Intel and the University of California, Santa Barbara have succeeded in bonding indium phosphide lasers to silicon so tightly that light generated in the indium phosphide layer is transferred into silicon light guides. However, such bonding is costly and cannot be integrated into standard chip manufacture. Silicon is a poor material that typically wastes energy, and researchers have had a difficult time controlling the crystals and the necessary materials needed for lasers to grow on top of silicon. At the University of California, Berkeley, principal investigator Connie Chang Hassan's research group has overcome the crystalline mismatches between silicon and the gallium arsenide compounds that have blocked laser growth. This breakthrough has allowed researchers to grow tapered hexagonal pillars of indium gallium arsenide with bases only half a micrometer across onto silicon chips. Chang Hassan said of the research, "Today's massive silicon electronics infrastructure is extremely difficult to change for both economic and technological reasons, so compatibility with silicon fabrication is critical. One problem is that the growth of semiconductors has traditionally involved high temperatures, 700 degrees Celsius or more. That would destroy the electronics. Meanwhile, other integration approaches have not been scalable." The semiconductors were grown using chemical vapor disposition in the same way that LEDs are created. Nanopillars act as lasers. When an external laser shines on the top, the laser light bounces around inside the pillar, following a helical path from top to bottom, where some of the light leaks out. Another key to making lasers on silicon chips is to not let the temperature get too high. Chang Hassan says that her process could eventually be used to grow high-quality lasers on otherwise finished silicon chips patterned with transistors and optical components, giving them the compatibility of encoding data into pulses of light. The unique approach of growing nanolasers directly onto silicon could lead to highly efficient silicon photonics. The researchers noted that the minuscule dimensions of the nanopillars, smaller than one light length on each side, in some cases make it possible to pack them into small spaces, with the added benefit of consuming very little energy. The unique advancement of nanolaser growing technology will help improve other optical sciences that are expected to flourish in the near future. Some of those being optical agriculture, 3D displays, solar power generation, optical cancer treatment, nano-optical processing, and much more. This research has had the potential to catalyze an optoelectronics revolution in computing, communications, displays, and optical signal processing. In the near future, researchers expect to improve the characteristics of the lasers and ultimately control them electronically for a powerful marriage between photonic and electronic devices. Clearly, the overall impact of this research will have an effect on multiple fields of scientific research. Nanolaser technology allows the possibility of supercomputers to speed up their already lightning-fast download capabilities and opens up better processing efficiency for companies like Intel and IBM who were previously using workarounds. However, the technology is still in its early stages and won't be readily available for some time. Also, there have been other recent advancements in computer downloading speeds, with Intel's 50 GBS chip, for example, can download an HD movie from iTunes or up to 100 hours of digital music in less than a second. The chip also uses silicon photonics and is seen as a possible replacement for copper wires to connect components within computers or between computers in data centers. Although there have been previous attempts to grow lasers onto silicon before, Chang Hassan's research group overcame the obstacles which were blocking the growth of lasers. This breakthrough will help change the future of silicon photonic technology and the wider use of photons in electronics.